My name is Francisca Annan. I'm going into my 4th year of the medical sciences program, and I work in the Thompson lab with Pyrrolic compounds. We work with pyrrole-containing compounds such as BODIPs, also known as boron dipyromethanes, which are a class of organic compound known for their intense color and bright fluorescence. They are synthesized from dipyromethanes, or dipurines, which are themselves synthesized from pyrrole, pictured here on the far right. In a BODIP, the dipyromethane is complex with a di-substituted boron center, and in an FBODIP, the boron center carries 2 fluorine atoms. Pyrrolic rings are commonly found in colored natural products such as bilirubin, the biopigment, and chlorophyll, both of which are pictured here, with the pyrrole rings highlighted in blue. Due to the COVID-19 pandemic, I spent May and June at home conducting literature review centered on chiral pyrrolic compounds, which had not been done by our group in a decade, so it was fascinating to see the kinds of exciting developments emerging in our field. In July, we returned to the lab and I was able to conduct some real experiments. Based on some of the previous work done within the group, the long-term goals of my work are to synthesize, isolate, and characterize an array of alpha-substituted and beta-substituted BODIPs for potential use in mass cytometry and photodynamic therapy, respectively. This summer, to investigate the synthesis aspect, I spent some time optimizing the conditions for a palladium-based catalysis involved in synthesizing one such alpha-substituted BODIP, pictured here on the left. The catalytic system includes a palladium precursor pre-functionalized with labile ligands listed first here as PD2-DPA3 and a ligand of interest, PAD3, that come together to form the active catalyst. Perhaps not surprisingly, increased amounts of each component resulted in increased yields of my desired product, suggesting that there is in fact a positive correlation between the quantity of the catalyst and the amount of product that the reaction is able to generate. Optimizing this catalyst system will allow me to synthesize similar compounds from my honors project more robustly. In preparation for the new semester, I also synthesized this funky-looking brominated BODIP, which you might recognize as the starting material for the previous reaction. The purified product is a shiny crystalline red solid that is kind of orange in natural light and has a green fluorescence under UV light that you can see pictured here. The synthesis challenged my troubleshooting skills, but I am super proud of the quality of the final sample. As you can see, I was super thrilled to be back in the lab in July. I was grateful for the opportunity to improve my lab techniques. The very first reaction I completed months back was this challenging 2-day synthesis of tellurafene, a compound not pyrrolic, but being used in one of my fellow graduate students' projects, and that I may use in my own honors project. The procedure was challenging, provided me with a lot of invaluable experience working with moisture and air-sensitive reagents, and helped me to familiarize myself with new equipment and undertake a long synthesis from start to finish. This one had over 40 steps. A purified sample of tellurafene is a clean yellow liquid as pictured above. The flask is a little frosty because my sample was stored in the laboratory freezer, but I think I did a great job. Here is my lab group, and thank